Let's do a physics example of a second-order linear homogeneous ODE with constant coefficients. Here's a fun example. So suppose you have a rope or a chain. The total mass is m, and the total length is L. And you've got part of it hanging off the end of a frictionless table. So that's important, frictionless. I want to know basically what is the position of this thing as a function of time. So as this chain is sliding off the table, how do I describe where its end is? So I want to know the position of this end point here as a function of time. Okay, so take a minute to see if you can try to visualize it. To help you start thinking about it, here's a kind of warm-up clicker question which I would do in class. Just thinking about, I just want to know what's the acceleration of the chain when part of it is hanging off, like in the picture there. So just part of it is hanging off the table. What's the magnitude of the acceleration of the chain? Is it bigger than g, less than g, or exactly equal to g? So go ahead and pause the video, spend a couple moments thinking about it, see if you can commit to one of these answers. In fact, the answer to that previous question is the acceleration magnitude is less than g. You might think that it would be equal to g because it's a frictionless table, but the key is that not all of the mass is being affected by gravity equally. So one trick to thinking about this is to break the chain into two pieces. You've got this piece, which is falling freely, or not falling freely, but it's being affected by gravity downward and there's no upward force. And then you've got this piece, which is being affected by gravity but is being supported by the table. So one way to think about it is you can kind of model this chain as two masses, one which is mh, which is a hanging mass, and then another mass which is on the table, mt. And they're connected together and there's no friction. And this is a problem that you probably solved in your intro physics courses. And maybe I won't go through the details of how it works. So you just draw a free body diagram here. You've got a tension force upwards, and then you've got mhg downwards, and then here you've got a tension force this way, same tension force acting on mt. And then you can write down Newton's second law for this. So F equals ma, that gives me the one on the top there. And then I can do a similar thing for the bottom. And I get those two equations, and the two blocks have the same acceleration because they're connected together. And you can combine these two equations together to solve for A. And I get A is equal to mh, the hanging mass, divided by the total mass, which is mt plus mh times g. So it's not equal to g, it's actually less than g because the numerator is smaller than the denominator. Okay, so now that's the simple example that I just did here with the two masses. Now the chain is trickier because as it falls, the masses are changing with time. So as the chain falls, more and more of it is hanging off the end, right? And less of it is on the table. So the acceleration is not constant, the acceleration will change as a function of time. Okay, so we kind of very briefly derived this equation for the hanging mass, but now we said in the hanging chain example, this hanging mass depends on time, which means that the acceleration also depends on time. The denominator here, mh plus mt, is just the total mass. Okay, so that doesn't change with time, so that's nice. So my acceleration is going to be however much of the mass is hanging over the edge as a function of time divided by the total mass times g. And now I have to think about how much of the mass is hanging off of it. Well, if the total mass is big M, and then the distance that is hanging off is x, I can figure out the mass that's hanging off. So the hanging mass is the total mass times the fraction of the chain which is hanging off. That's this part here. Right? This is the fraction of the chain which is hanging. If x was L over 2, then half the chain would be off and half the chain would be on, and then the hanging mass would be half the total mass. So this makes perfect sense. So I've derived a differential equation. It's this: A is equal to big M times x over L divided by the big M times G. Those cancel. And I get the following differential equation, because A is x double dot is equal to G over L times x. Or I could write it like this: x double dot minus G over L times x is equal to 0. So this right here is a second order ODE, homogeneous, constant coefficients. And so to be able to determine the position of the chain as a function of time, I have to solve this ordinary differential equation. So let's get started doing that. To solve this question, we need to solve this ODE. And it's exactly the kind of ODE we've been talking about in this lecture, so you know how to proceed. Whenever you encounter one of these ODEs, you make a guess. So we're going to take a guess. And the smart guess is to guess x of t is equal to e to some r times t, and r is a number. And then we have to determine what r is. Okay, so same steps as before. X dot is r e to the rt, and x double dot is r squared e to the rt. Plug it into the ODE. What do I get? I get r squared e to the rt minus g over L e to the rt equals 0. And like always, you know you did it right. If there's an e to the rt in every term, you can cancel those. So I get r squared is equal to g over L. And so r is equal to the square root of g over L. But there's supposed to be two solutions, right? Where did I screw up? I forgot the plus and minus. So take the square root, have a plus or minus. So I've got two solutions: plus g over L, minus g over L. And so now I've got my general solution, which I form by taking those two, right? I've got those two solutions. x1 of t is e to the plus g over L times t, and x2 of t is e to the minus square root g over L times t. Both of those solve the ODE. The general solution is any arbitrary combination of those two: a e to the plus square root g over L times t, plus b e to the minus square root g over L times t. So this is going to be my x of t. So there's a general solution for the position of this chain. It's got two arbitrary constants because it's a second order ODE. And now, as usual, you'd have to determine those arbitrary constants by plugging in some initial conditions. So maybe I will think about now applying some initial conditions to solve this in general. So just to finish up this problem, let's try to think about what are the physical interpretation of A and B. So let's apply some initial conditions. Let's take x of 0 is equal to xi, some initial position, and x dot of 0 will be the initial velocity. So we'll try to solve it in general. I want to know a and b in terms of xi and vi. So I'm going to get two equations. The first one is going to be xi is equal to a e to the 0 plus b e to the 0, right? So I'm plugging in t equals to 0 into my equation for x. It's got to be equal to xi. The second equation, I got to take the derivative. So I need x dot of t. So it's a square root g over L e to the square root g over L times t plus b minus square root g over L. These are from the chain rule, these factors coming out here, minus square root g over L times t. So applying my second initial condition, I'm going to have vi is equal to a square root g over L plus minus b square root g over L. So I've got two equations, two unknowns, solve for a and b. Okay, so again, it's an algebra problem, and let me just skip to the solution. So there you go, I just did some algebra combining those two equations 1 and 2 and solved for a and b. So it's a little ugly. A and b each depend on the initial position and velocity. And so now we can, if we want to get a final formula altogether, we can just substitute that back in to the equation for x. So let me just collect everything together on one last slide. So on the previous slide, we had related a and b to the initial position and velocity of the chain. So I'm going to have everything together. Let me just write it all. xi is a, which was 1/2, xi plus square root L over g times vi, e to the square root g over L times t, plus 1/2 xi minus square root L over g times vi, e to the minus square root g over L times t. So there's the equation describing what that chain is doing, what this position, this point of the chain is doing as a function of time for any initial position xi and any initial velocity vi. I would be able to tell you exactly what that chain is doing as a function of time. So that's a surprisingly tricky problem for such a simple physical system, but it all relies on the same techniques that we use to solve second-order linear homogeneous ODEs with constant coefficients. You guess e to the RT, you get the characteristic equation, you get the two solutions, you form a linear combination of those two solutions, and then you plug the initial conditions in to finalize your answer. All right, so I've got a few more loose ends to wrap up in the next set of slides, but then otherwise we'll be able to move on to a different topic.